distance. The value here of k is called the drag coefficient. But we have k in other places too, right? So if you're thinking, well, it must be like a spring constant because we use k for both of those. No, not at all. We just need something here, something to hold this place. Drag behaves differently. When we talk about drag, I'm going to use coffee filters as my example. Drag is about how the force of the atmosphere or fluid affects the motion of the object. But for something to experience drag, based on either one of these forms, there has to be motion of the object. Right? Drag is based on how fast you're moving. There's different kinds of drag, and we generally focus on linear drag, but you can have some kind of functional drag, something where there's a function of the velocity that determines how much drag there is. The most common problem has been the coffee filter problem, a problem where you drop a coffee filter and you're supposed to determine how it behaves due to its drag. But there's been different versions of it. There's been a problem a couple years ago where they had a container filled with some viscous fluid and they were dropping marbles into it or BBs into it. And when the BBs made into the fluid, the viscosity of the fluid caused an upwards force, not a buoyant force, just an upwards force of drag against the weight of the marble. And it was proportional to the velocity. Don't be turned off if it's not just a coffee filter, even though that's the more common question and that's the lab we're going to do. Any one of these things, anytime an object experiences a force that is proportional to the velocity, you're going to have a more complicated solution. A couple years ago, there was a problem where an object had an initial velocity of v0 and reached a section of the ground where it experienced a drag force that was proportional to the velocity. Like this. It was traveling horizontally, so there was no weight pulling it down or pulling it over, but it had some initial velocity and was eventually going to be brought to rest by this drag force. The reason I'm bringing all of these up is because when you deal with something that's experiencing drag, the dynamics of the problem are more complicated. For example, when we first drop an object that's experiencing drag, by saying we're dropping it, we're beginning when the object has a velocity of 0. So it experiences no drag force when it's first dropped. It's going to accelerate because there's an unbalanced force acting on it. And an instant later, because it had a downwards acceleration, it developed a velocity. And now that it has some velocity, so it has, some small velocity downwards. Now there is a drag force upwards. Now that continues because the forces are still unbalanced. The weight doesn't change necessarily. But because it's been allowed to accelerate downwards for a little bit more time, the velocity has now increased. And that has increased the drag force. Well, there will be a moment, even though the weight may not be changing, there'll be a point where the velocity will have increased enough so that the upward force and downward force are balanced. We call this the point at which terminal velocity is achieved. When you achieve terminal velocity, the net force equals 0. So for an object experiencing laminar drag or linear drag, the terminal velocity is reached at this moment. And therefore you can kind of calculate it if you know what k is. The problem is, what is k? And that's elusive. That's the thing that I want to start our conversation about. Just because we put some proportionality constant doesn't mean that we have a handle on what k is about, or that there even is a way of expressing k. The actual physics problem that I want to address is the one that isn't just about terminal velocity. The one I want to address is the one that asks you to find v as a function of t for an object experiencing drag. Doesn't matter which version of drag we're talking about, v as a function of t requires you to solve a first-order differential equation. And so to do so, you need a certain set of skills, and that's what we want to talk about today, that set of skills required to do this. We've talked about this first semester, and I said we would come back to this second semester. Well, as you might have guessed, it's now second semester. We're going to focus on linear drag, and we'll do quadratic drag later. Both of these have been on the AP exam at some form or another. So we'll have to learn how to use both. But today, we're going to focus on the top one, linear drag. Okay? So to do so, I want to start by going through the steps required to get our solution. And I also want to, at the same time, assign the point value for each of the kinds of things you will have to do so that you can understand where your time should be spent. The most likely question will sound something like this. Set up, but do not solve, a differential equation that could be used to find the velocity as a function of time for the coffee filter. After you do that, the next thing will say, now using integral calculus, solve your differential equation and show that the velocity equals, and they're going to give you the function. Everybody understand? It is very likely you will not have to do what we're about to do on the exam. And you'll see why they've kind of manipulated the exam to keep you from having to do this. Some of you already know how to do this. Yay, you. If you're in E&M, this is the exact same thing we've already done for a capacitor. So it is the charging equation for a capacitor. But for you guys who've never done this before, I'm going to be deliberate. I'm going to go through each step meticulously, probably taking longer than is necessary, but I will expect you to be able to reproduce it perfectly. Does everybody understand? All right. To start with, we're going to deal with linear drag today. So the very first thing you need to do when asked to produce a differential equation is you need a place to start, something that has a differential. And the best place to start is always force. You'll probably get a point just for using Newton's second law in the beginning of your function. And then recognizing that the acceleration is the differential. That'll probably be also worth a point. Now, using what you already know about net force and your differential, you need to produce an equation. We're using this. This is where we are right now. Somewhere after the object has been released and is experiencing two forces, mg downwards and kv upwards. But that has to equal m dv dt. That's your differential equation. Setting up the differential equation will be worth 2 to 3 points on the exam. If you're asked to create a differential equation, they often give you a point for using Newton's second law and a point for substituting in dv dt. They don't always give you a point for getting the forces correct on that problem. Now, after this will be, because if they don't say to solve it, don't solve it. Stop here. This is a differential equation. You don't have to go any further if this is what they ask you to do. But if they say to solve it, you should at least do these next couple of steps. The next couple of steps require you to split the differential. So although I'll draw a line here indicating that's usually the end of the first part, splitting a differential is just algebra. So we've talked about how to do this before. Let's go through it again. It involves you just doing a little bit of manipulation. First, multiply both sides by dt. That splits the derivative. So you'll get mg minus kv times dt equals m dv. Now step 2 requires that you collect like terms. So that means you have to figure out what your important terms are. T is one of them, and V is the other. So any part of your function containing T has to be brought to the same side as dt, and any part of your function containing V has to be brought to the same side as dv. For our functions, that will be relatively easy and will be done generally using a little bit of multiplication or division. In this case, we'll divide both sides by this, getting V on the same side as dv, and noticing that t is not represented anywhere, so I don't have to move anything to move t. So that's going to give me dt equals m over mg minus kv dv. Now, there's one more step, which is to set up your integral. And apply limits. All this really means is to draw in your script fancy S to indicate you're doing a summation. But to get the point, they want to know that you understand the boundary conditions for the problem. Now, I am familiar with the fact that you guys in AB and BC are taught to do your work as indefinite integrals and then put a constant after you're done doing your work, and then plug in your boundary conditions at the end to figure out the value of the constant. Every single scoring guide for the physics exam shows definite integrals with your boundary conditions placed at the point of the integral symbol. You don't get points taken off for not doing that, but I would encourage you to do it this way because it's not any more work and it ensures that you get the points because that's where they're supposed to be. Does that make sense? So generally, you'll be given the bottom numbers to put here. And those bottom numbers are whatever your initial conditions are. For example, at time 0, the object's velocity was 0. The left side will be whatever the time is, the right side will be whatever the velocity is. So whatever your opening conditions are. The top are always going to be functional variables. We are trying to find a function. So the top is always going to be to a functional variable. V for the side with V, T for the side with T. You don't put in a future condition here. Like, we know we're going to reach terminal velocity. We know what terminal velocity looks like. You don't put that in here. You put in a functional variable because we are trying to find V as a function of T. So our integrals have bottoms usually, but don't have a top variable. Now, if you can make it to here, usually you can just write the answer after this. And they will have likely given you the answer, and you'll get all the points. Meaning they don't want to award points for just doing all the algebra necessary to get the answer. We're going to do all the algebra necessary to get the answer, so you can understand what you're probably not going to have to do on the test, but I want you to be able to do it. Everybody understand? So we're going to do the calculus today. Now, it is a little bit of calculus. And again, many of you just had a test on how to do this, so you should be experts. You should all be able to do the left side anyways, because we did the left side first semester. The right side, on the other hand, maybe not. So let's talk about the left side. There is no variable on the left side. So if there's no variable, we assume there is a variable, t to the 0 power. We force it to be a polynomial function because there is a 1 there. So we've just now explicitly stated that that 1 is t to the 0. From here, we do the antiderivative and apply our limits. That's how you do an integral. The antiderivative of t to the 0 is t to the 0 plus 1 divided by 0 plus 1. You guys know the polynomial rule. Add 1 to the exponent and then divide by the new exponent. And we have limits 0 to t. Once you have found the antiderivative, and that's the first step, antiderivative, your next step is to apply your limits. Sometimes you may want to simplify. So I'm going to go ahead and simplify, because my simplification is t. Applying your limits means put t in first, the top, you put whatever your top boundary in first, then subtract and put in your bottom boundary. And you're done. That's the calculus. So Let's do the other side. Well, the first thing I would point out to you is that we want to try and find a way to make the other side look like other integrals, other antiderivatives that we know how to do. Unfortunately, we don't have anything that looks like this. We've not done one like this before. We could take the m out because we can take the constant out of an integral, and maybe that will simplify it some. But I think you guys are probably pretty familiar with the fact that we probably just can't do this. It doesn't look like a polynomial, and all you guys have learned is the polynomial function. Now, you do have an integral table with lots of other integrals, but there are 4 basic antiderivatives you need to know. There's this one, the inverse. There's cosine, there's sine, and there's the exponential. You'll need to know these 4 outside of the polynomial. They're on your equation sheet, so you can just look them up on your equation sheet. There's a few others on your equation sheet as well, but these are the only ones that ever show up. This, although looks like a polynomial, u to the -1, if you try your polynomial function on it, it won't work because it'll give you u to the -1 plus 1 divided by -1 plus 1, which divides by 0, so it doesn't work. So you guys who don't have calculus, now you know why that's not going to work. People in calculus already know that. They know that this antiderivative is natural log. This one's just funny, but it's not funny if you understand how trig works. The antiderivative of cosine is sine, and the antiderivative of sine is minus cosine. Right? You guys all know those, right? Or it's cosine with a phase shift. You can always write it like that. The negative sign there is about the fact that it's shifted. And the antiderivative of e to the x is e to the x. If there's a coefficient there, you just divide by the coefficient. Basically the chain rule. These you'll need to know. These come up. This one not so much, but these for sure. Now, that being said, that still doesn't really help us with what we have over there to the left. What we have over there to the left doesn't really look like any of those things I just put up there. And that's because we have a complex function in the denominator. Now, it seems to me that although it's a complex function in the denominator, we could probably recognize that it kind of looks like an inverse, but with more stuff there. This is where a process comes in to try and substitute a new function in for the function that's there. This is called U substitution and is basically the opposite of the chain rule. So those of you who have learned derivative calculus know what the chain rule is. U sub is the opposite of the chain rule. It's how you work the chain rule in reverse. And it requires that you pick something to sub in for your function. I'm going to sub in for mg minus kv. Because if I do that, I will get a function that looks like something I know how to work with. I'll get 1 over u. The problem is I can't change just the function because I'm taking the derivative with respect to dv. So I need to replace dv at the same time. To do that, I have to take the derivative of du with respect to my functional variable v. So I need to find du dv. Well, the derivative of mg, which is a constant, is 0. Right? None of those function variables have v in it, so the derivative of mg is 0. I can use the polynomial rule on kv, because that's kv to the 1 power. So that's minus k, bring down the 1 times v to the 1 minus 1. Taking the derivative, so I do the opposite. You bring down the exponent and subtract 1 from the exponent. Of course, all of that just comes out to be 1. So du dv is just minus k. Now, again, we need dv, so cross multiply, and I'll get that. So plug that in for dv. That's u substitution. Now, if you're taking calculus, they would also have you change the limits of integration here to match u. I don't do it that way, but we could. We could put in v and have our new limit, and then put in 0 and have our new limit. So since I did it the other way in my other class, I'm going to change the limits. So when I put in v, for v in my substitution, I get mg minus kv as my top limit. And then I'll put in 0 for v for my bottom limit, and I'll get mg minus 0, or just mg. So I've just changed my limits. That's u sub. That's how u sub works. The first thing I notice is that I have a new constant sitting in here, minus k. I can just take that out because it's a constant. So I'm going to get m over k in the integral of 1 over u du. So this one's easy now, right? It matches exactly what we know. So we can go ahead and take the antiderivative and get, oops, I forgot my negative there. Don't let me forget my negative sign. Thank you. You're the best. So I'll get natural log of u, but I have to evaluate this from mg to mg minus kv. Everybody good so far? Following along? One more step, and the calculus is done. So we got to plug in our limits. So negative m over k, natural log of mg minus kv, minus natural log of mg. And that's it. All the calculus is done. That's not the answer. That's the calculus being done. But remember, you're supposed to find v as a function of t. So now all you have to do is tease out v. You guys know algebra. This is just algebra. So I can count on you to do this. Would you like me to do it with you the first time? Or do you think you can do it on your own? If you think you can do it on your own, you should be running and going and doing it. I know that some of you can't do it on your own, or at least not without a lot of help. So I'm going to go step by step with what happens next. But you guys know what to do. You should be almost done. I want v by itself. It's buried. You guys see that it's buried, right? So the first thing I'm going to do is probably start unburying it. So I'm going to multiply by k over m. So I get negative k over m times t on the left. And that gives me natural log of mg minus kv minus natural log of mg. Now I know that you can get rid of a natural log by raising both sides to a base, the base e. To make that easier on me, I know that natural logs are just exponents. So when I subtract exponents, I can divide. So I can write this as mg minus kv over mg. I'm under the impression you know these rules for logarithms. The next thing I can do is I can raise both sides to the base of e. That will get rid of the natural log and free the value of v from inside a log. My next step, of course, is to, multiply both sides by mg. Seems like a reasonable thing to do. I think I could do some basic algebra to get kv by itself. I'm going to factor out an mg first. And now I will divide both sides by k. There it is. They would have given this to you. And they'll say, show that velocity as a function of time is in this form. But you could also do the work. I didn't skip many steps. I was pretty explicit. I'm not sure there's a lot of steps to skip, but I want to point out this is worth most of the points. It is possible that you can go from here to here and get all of the points because they're not necessarily interested in your ability to do algebra and calculus. They want to know that you understand where it comes from, but also, how many minutes is that? Even if you're fast? 2 or 3? You're working at a point of 1 point per minute. And this is all only going to be worth maybe a point. So what I'm telling you right now is if you get this problem, you come back to this, right? Take the answer, do what has to be done for the rest of the problem. But if you have to show all this work, come back to it. Get the rest of the problem done first and handled, because this is busy work. And you don't want to be distracted by it, and you especially don't want to make a mistake. They gave you the answer, right? So go on, do the work that's next. Because if you make a mistake in the middle of this, you are wasting precious minutes. So that's the first thing I'll tell you. I want you to be good at it. I want you to be able to do this. I am going to test your ability to do this. Okay, I want you to know that I'm not going to leave this without it being done. I'm going to test your ability to do it. But I want to focus here. Right? This is where the points are. And this shows you understand the nature of the physics portion of this, which is what's more important to me. Not that you're excellent algebra students. Let's go to this for just a minute, though. Since I have a few moments, do you notice what this is? You should from the very beginning. What is that? That is the terminal velocity. That's right. Of course it's here. Now, look at the way this function looks, please. What do you get when you put in 0 for t here? What does this term become? 1. 1 minus 1 is? 0. So clearly, v at t equals 0 is 0. It had to work this way. We set that as our initial conditions. When you set those conditions, your function is going to do that. It's a way to test to make sure you've done your math right. However, what is that term when t goes to infinity? What's that? No. This term becomes 0. Right? It's 1 over an infinitely large number. Well, that's important for a number of reasons. Look at what this tells us. At infinity, the velocity becomes the terminal velocity. Right? Because that term goes to 0. 1 minus 0 is 1, and we get the terminal velocity. I know you guys tend to think that infinity is a big number. It's not. Infinity is just big relative to the other variables. How long did it take for the single coffee filter to hit terminal velocity? Right, well under a second? So don't think that infinity means big. It means big compared to the other numbers. That's all it means. We reach terminal velocity. We do it all the time. Anytime you drop something, it will reach terminal velocity and will probably do so in under a second, which means in those cases, milliseconds is infinity for the concerns of the problem. I need you to do one more thing though, and this will involve your calculator. Turn off your stat plots. If you're in stat, you probably have them all activated. And using your plotting function of your calculator, I would like you to plot these three things. Try and get them all on the same graph, so they're all on the screen at once. You should be able to predict this, but you need to see what these functions look like. Go to the zoom function, make sure you zoom standard or zoom whatever will give you a good view of all three functions. Done yet? We know all the functions start at 0. You should have something that looks like that. But you should also have something that looks like this. And something else that probably looks like, right? They all reach this asymptotic point at different times. You manipulated that with this number. So does making this number smaller make it get there sooner or longer? You should understand how that works. Okay, I want you to understand how that works. Yes, if you make this number smaller, it takes longer to get there. That shouldn't be a surprise. K is in the numerator, right? K is in the numerator, has a larger drag coefficient. It will take longer to get to that point. And if K is smaller, it'll get there sooner. But notice they're all asymptotic. Just because you see an exponential doesn't mean that your function decays. It doesn't mean that it's exponential growth. This is an asymptotic approach to what is the terminal velocity. All right.